this is the inverted pendulum robot. This is obviously the pendulum, which is attached to an axle. Attached to the axle is a rotary code wheel, which is essentially just a plastic disc with a bunch of slits on it, 800 for this one. Sitting right on top of an optical encoder. The optical encoder basically has an LED, which is constantly on, and a phototransistor, which senses whether light's being reflected back to it or not. Obviously black absorbs light, so you're going to get a digital readout of 0. So the optical encoder has two channels, A and B. They're offset by 90 degrees. Both of the channel information gets sent to the microcontroller, which is the Arduino Nano. That information is used to determine things like speed, direction, position, all that. And then based on the code that we're currently using, that information gets processed and it decides what the next best course of action is to get the pendulum, obviously, to the top. This information is then sent to the motor driver, which controls the motors.
So for the control structure for this robot, we decided to use a super loop so it will continually execute. In the context of the super loop, we use spin locks to wait for certain functions to occur. For the first phase of our robot, we use the velocity of the shaft to control how the robot moves. The velocity of the shaft is calculated based on the encoder pulse width that you can see here on the oscilloscope. The pulse width gives an idea of the velocity of the shaft, which is then sent to the spin lock. So it waits until the velocity changes direction. So when it goes from a positive velocity to a negative velocity, or from a negative velocity to a positive velocity, it passes the 0 point. At this point, we then change the direction of the robot. For the second phase of the robot, we use a PID control loop. A PID stands for proportional integral derivative. How this works is that we set a set point for the PID. In this case, since we have an 800 count encoder wheel, we decide to use 400 since that's exactly halfway around the encoder wheel when the pendulum is balanced exactly up and down. We set the set point to 400, and then the farther away we go from 400, the more gain is applied to the motors. The proportional component of the PID is basically based on how much error we have from the actual value and the set point. The derivative is a smoothing factor so that the robot doesn't try to overcompensate when the pendulum is almost balanced, causing it to fall out of balance. To actually control the motors, we decided to use a motor driver rather than a motor controller. Since this has a higher update frequency, we can drive the motor driver with a direct PWM signal. PWM stands for pulse width modulation, and basically you control the power an element absorbs based on the width of the pulse that you send to it. This is an easy way for the microprocessor to control the amount of power sent to the motors. The pendulum, when it starts to fall, we can't get enough velocity quick enough. So the pendulum just falls around, and then we can't recover from that. Another issue we had is that the motor gearbox stripped out, so one motor is moving differently than the other one. This causes the robot to not function the same way every time, as the gears react differently.